Where do real numbers come from? What I learned in middle school was the real numbers are like the rational numbers, except they also include the irrational numbers. It's very helpful. But one day, during what I can only describe as a mathematical midlife crisis, I realized I had a problem with all of this. Sure, I understand that x squared equals 5 has no rational solution. But does that mean it has an irrational solution? Who says it has a solution at all? Are we allowed to just invent a new kind of number just because we really want to take square roots? And later on in real analysis, I learned that the real numbers are supposed to be like the rationals, but better. They have this magical least upper bound property, which is the backbone of half the course. But again, who says such a number system exists? Does it contain the rationals? Does it behave similarly to the rationals? How does this all work? This is where many students meet something called a Dedekind cut, which sounds like a painful surgical procedure, and the way some textbooks present it, it turns out to be pretty accurate. And at best, it just seems like some sort of mathematical formalism used to justify the real numbers with no real insight. But Dedekind cuts are not arbitrary. They're not some weird technical sideshow. By the end of this video, I will convince you that these are a really natural way to define real numbers that make perfect intuitive sense. Now, how did I get to this point? In the midst of my despair, I went to Nick, our resident animation wizard and mathematical grown-up, and I poured my heart out to him. I told him I wasn't sure I believed in real numbers, and the more I thought about it, the worse things got. I wasn't sure I believed in rational numbers either, or negative numbers, and in my darkest moments, I wasn't sure I believed in zero. I told Nick I was comfortable with positive integers, and that was it. Everything else had to earn its place and justify its existence. So in this video, starting with just the positive integers and some basic set theory, Nick and I are going to rebuild the entire number line. First, we'll construct the signed integers, then we'll construct the rational numbers, then we'll see why the rational number line still has holes in it even though it's dense. And finally, we'll use Dedekind cuts to construct the real numbers in a way that actually matches our intuition. By the end, zero, negative numbers, fractions, and irrational numbers will no longer feel suspicious. They'll seem inevitable. And as a bonus, we'll prove that 13 really does have a seventh root, which is good because I've been very worried about that lately. So let's get started. I told Nick I believed in the positive integers and some basic set theory. How was he going to invent signed integers? One approach you could take is to represent signed integers as ordered pairs of positive integers, where the idea would be that 5, 3 represents 5 minus 3, which is positive 2, and then he could use 3, 5 to represent negative 2. 7, 7 would represent 0, and so on. Now in this system, he could represent positive 2 many different ways, and in fact, every integer could be represented in infinitely many ways. Now this presents a couple problems. The first issue is that it seems wrong to have multiple ways of representing the same integer. And how do we know if 7, 10 is equivalent to 14, 16, for instance? Or in general, how do we know if A, B is equivalent to C, D? And if we're going to start using ordered pairs to represent positive integers, do these new positive integers behave in exactly the same way as they used to? How do we add them or multiply them? How do we know if two ordered pairs of positive integers represent the same signed integer? Well, it is tempting to say that we can just check to see if A minus B is the same as C minus D, but the whole reason we're in this mess is that due to my existential angst, I don't know what it means to take 7 minus 10 or 14 minus 16. But since Nick already knows where this is all going and he remembers his basic algebra, he can just say that these ordered pairs are equivalent if and only if A plus D is equal to B plus C. So 7, 10 is equivalent to 1, 4, but it's not equivalent to 4, 1. But 4, 1 is equivalent to 5, 2. Now it's easy to check that this relation is reflexive, symmetric, and transitive, so we know that it partitions the set of ordered pairs of positive integers. So the way we represent, for example, negative 3 isn't just 10, 13, it's the entire equivalence class that contains 10, 13. We'll write that as 10, 13 with a line over it, which of course is the same set as 1, 4 with a line over it, which is the same as 5, 8 with a line over it. And likewise, each representation of an integer corresponds to an equivalence class of these ordered pairs. None of these classes overlap, and in aggregate they contain every possible ordered pair of positive integers. The next issue is figuring out how to add and multiply these classes. It turns out that addition is easy. If we want to add a comma b to c comma d, we just add component-wise and get a plus c comma b plus d. We can check that this corresponds to the algebra we knew 10 minutes ago and pretended to forget. But we have to check to make sure this all makes sense. Let's say that instead of using a comma b as the representative from that equivalence class, we use a prime b prime instead. And the same for c comma d. For example, if we wanted to add 6 comma 10 to 7 comma 1, we get 13 comma 11, which matches Nick's assurances that -4 plus +6 is +2. But if we swap out the first pair with an equivalent one, say 10 comma 14, and we replace the second pair as well with an equivalent pair, say 9 comma 3, and add them, we now get 19 comma 17. But notice that this matches our previous answer, since 19 comma 17 is equivalent to 13 comma 11. In general, if we want to add the classes corresponding to a comma b and c comma d, we get a plus c comma b plus d. But if we use two equivalent representations of those classes, we get a prime plus c prime comma b prime plus d prime. Now we know that a plus b prime must equal b plus a prime, and we also know that c plus d prime equals d plus c prime. Add these two equations together, and we get that a plus c plus b prime plus d prime equals b plus d plus a prime plus c prime. And if we group together the terms like this, we can see that a plus c comma b plus d equals a prime plus c prime comma b prime plus d prime. So if we use different representatives from the same two equivalence classes, we get the same result. Now we have to answer the question of how to multiply these classes together. Back in algebra class, we learned that a minus b times c minus d is ac plus bd minus the quantity ad plus bc. This suggests that I might define multiplication as a comma b times c comma d equals ac plus bd, comma, ad plus bc. Again, we have to make sure this makes sense when we swap in different representatives for the same equivalence classes. Let's say we swap out a comma b with an equivalent ordered pair a prime comma b prime. We'll show that if we swap out an equivalent representation for that first number, we get the same answer. You can just as easily show that we can swap out an equivalent representation for the second number too, and therefore we can swap out both numbers consecutively and be confident that we'll get the same answer. Let's quickly write out this proof. We can actually carry out the multiplication the way we defined it earlier, and we need to see if these two equivalence classes are equal. So to check this, we add together the two outer terms, rearrange a bit, and factor, and we use the fact that a prime plus b equals a plus b prime. Multiply out and rearrange, we get the sum of the two inner terms above, which tells us that yes, the two equivalence classes are the same. Now we should check a few other things. For instance, if we just take two positive integers and add them the way we already know how, and then we turn each of those numbers into their new representation as equivalence classes, and then add those two equivalence classes, we indeed get the representation of a plus b. Other things we should check. If we take the equivalence classes corresponding to 5 and 7, for instance, and multiply them together, we get the equivalence class corresponding to 35. We should check the usual properties of integers still hold. 0 and 1 work just like we expect, even on negative numbers. None of these are hard to prove, they're just a bit tedious, so we're going to skip over them. It's easy to get lost in the weeds here, but let's take stock of what we've done. We started with positive integers and the usual addition and multiplication operations on them. We created these new entities and gave them cute little names like -1, 0, +2, and so on. And the new entities corresponding to our old positive integers behave just like the old ones did. As a physicist would say, there's no experiment you can do that can differentiate between the old and the new positive integers. To make things even better, these new negative numbers, and what we're calling 0, behave in exactly the way we want. So I think it's fair to say that we have constructed the integers out of just the positive integers and some sets. And if you followed this so far, I have some good news. The constructions that follow are actually simpler than this one, and they have a more intuitive structure to them. Now that we have the integers, how do we construct rational numbers? The straightforward answer that may have occurred to you is to represent a rational number as an ordered pair. And of course, there are multiple representations of the same rational number, so we have to take all of them. You'll remember from algebra class that a over b equals c over d if and only if AD equals BC. Or as they used to say, about 100 years ago, the product of the means equals the product of the extremes. So we'll say that two ordered pairs are equivalent if the product of the outer numbers equals the product of the inner numbers. And you can easily show this is an equivalence relation, so it partitions the set of ordered pairs of integers where the second integer is non-zero. Now, one weird thing to think about is that in this setup, a fraction is a set of ordered pairs of signed integers, and each of those integers is a set of ordered pairs of positive integers. So a rational number is an equivalence class of ordered pairs of equivalence classes of pairs of positive integers. We need to define addition and multiplication, and just like earlier, we already know what we want the answer to be. So we can define the addition of these equivalence classes just like you'd expect, and do the same for multiplication. We now have to make sure these operations are well defined. In other words, if you use two equivalent representatives of the same equivalence class, you get the same answer. It's a good exercise to write out these proofs, but we won't bore you with this. Now, just like earlier, we should make sure that these new objects behave the same way as our old ones did. We should also check the usual properties of rationals, like commutativity and associativity of both operations, and that multiplication is distributive over addition. And we can even show that our new set forms an ordered field. What's a field? It's just a set with two binary operations that behave very nicely with each other. We'll list out the properties, but honestly, whenever I try to remember what they are, I just mentally run through the properties that Q has. And an ordered field is a field with a relation that we'll call less than, which has the usual properties that we're used to from dealing with rational numbers. The one that might look unfamiliar is trichotomy. This means that if you take any two numbers, they're either equal or one is less than the other, and furthermore, only one of those is true. How do we define this relation in the case of the rationals? We can just say that x is less than y if 0 is less than y minus x. And we say a rational number is positive if it can be represented as an ordered pair of two positive integers. And of course, to be thorough, we should check to make sure that this definition of less than complies with the requirements we have above. And we should make sure that these new whole numbers, which consist of an integer paired with the number 1, still behave the same way. Now for the main event, how do we construct real numbers? Now, it's worth asking if rational numbers are really missing anything. You might argue that since the square root of 5 isn't rational, there is some other irrational number whose square is 5. But my question is, who says that 5 really has a square root? If no rational can be squared to get 5, then maybe that's the end of the story. But it occurred to me one day that there's a very good reason to believe in the square root of 5. You can partition the rationals into two parts. The first part would have all the negative rationals plus the non-negative rationals whose square is less than 5. And the other part would have all the non-negative rationals whose square is greater than 5. So if I can tell you all the numbers less than my mystery number and all the numbers greater than my mystery number, I think it's fair to say that this number is in some sense real. In fact, that's exactly how you can construct the reals. You can just say that a real number is a partition of Q into a lower half and an upper half. This type of partitioning of the rationals is called a Dedekind cut. Now, there's no reason to carry around two pieces of Q if one is just all the stuff to the right of the other, except for possibly the point in the middle, so we'll just work with the left half. So we'd love to define a cut as all the rationals less than a given real number. But this is a circular definition since we haven't yet defined what a real number is. Let's try again to describe this just in terms of the rationals. We want to say that a cut of the rationals is the left half of the number line if we break it somewhere. So the first requirement is that we don't want our set to be the empty set, and we don't want it to be all of Q. That's because the empty set would have to represent negative infinity, all of Q would have to represent positive infinity, and we do not want to include those in our construction. Next, we need downward closure. That is, anytime the set includes one rational, it also includes everything to its left. Finally, we don't want it to have a greatest element. In other words, it does not include its right boundary. So for instance, the negative rationals form a cut. If we include 0 in that set, it now has a greatest element, so that's not a cut. And the open interval from -1 to +1 is not downward closed, so it's not a cut either. If you give it some thought, I think you'll agree that this captures our idea that a cut should consist of every rational number to the left of some imaginary boundary. Now, the idea is that each regular old rational number would be represented by a cut that just consists of every rational number to its left. And if you want to represent something else, like the square root of 5, you would take everything to the left of where this purported number is supposed to be. Anytime you have a hole in the rationals, just grab everything to its left, and that's how you can identify the hole. Now, the super cool thing is that we can define one cut to be less than or equal to another if the first is a subset of the second, and it's strictly less than if it's a proper subset. And oh yeah, we should explain how to do basic arithmetic on these new objects. Addition is easy, just add together every pair of numbers from each cut. You can show pretty easily that this gives the expected result for rationals. If I take each of the rationals to the left of 1 and add them to each of the rationals to the left of 2, I get all the rationals to the left of 3, and only those rationals. A good, though mildly annoying exercise is to show that the result of adding two cuts gives us a new cut. For multiplication, well, let's start with multiplying positive numbers. And by positive numbers, I just mean cuts that contain some rationals greater than 0. To multiply them, we multiply together every pair of positive rationals in our two cuts and take everything to the left of that. You can then write down rules for handling a negative times a positive and a negative times a negative. And at this point, a good analysis student is itching to show that this process of multiplication gives us a new cut and that the rational numbers still behave the way we want. And there are a zillion other things to check at this point. And while it is tedious, I hope the general idea is clear. These cuts behave just like you'd expect real numbers to behave, and they behave exactly as rationals already do behave. So we've constructed an ordered field that contains things that behave just like rationals, but they include these other things as well, which we're calling holes in Q, otherwise known as irrational numbers. But before we declare victory, we should ask, does this new set have the least upper bound property? That is the whole reason we're here today. Recall that this property says that if we take a non-empty set of these elements that has some upper bound, then there must be a least upper bound, though possibly not in our original set. So for instance, in Q, the numbers strictly less than 1 have a least upper bound of 1. But the whole problem with the rationals is that sets like this one don't have a least upper bound. But it's actually really easy to take the least upper bound of a set of cuts. Just take the union of all those cuts, and you get a new cut that by definition contains as subsets all the other cuts. It's not tough to show that if your initial set of cuts is non-empty and bounded above, then the result of this procedure is a new cut that is actually the least upper bound. I love this construction because the final step seems simple once everything is set up right, but historically, it took mathematicians a long time to get all this organized and straightened out. Okay, you want the basic idea behind the proof? First, it's a straightforward argument that when you union together a non-empty set of cuts, you in fact get a cut, unless you end up with all of Q. Since there's an upper bound to all these cuts, that means there's a rational number that is not in any of them, so our union can't be all of Q. Now we have to argue that this new cut is in fact an upper bound, but that's simple since it contains every one of those cuts as a subset, and that's what it means for one cut to be greater than or equal to another. And finally, to show it's the least upper bound, imagine you took a smaller cut. Then it would be missing some rational number that was in the union, but that means it's absent from all of the C sub alphas, so it's not an upper bound at all. Now, what if we want to take the seventh root of 13? We can just look at all the positive rationals whose seventh power is less than 13 and take the least upper bound. And instead of least upper bound, we write sup, which stands for supremum. This does leave the question as to whether this really works. We know there is definitely a least upper bound of this set, but does this number raised to the seventh power actually give us 13? Well, it does, but the proof takes a little work, and I've already been talking a long time, so we'll put it in a separate video. The important thing to remember is that we can construct the reals in a fairly intuitive way from the rationals, and they have the least upper bound property. The rationals can be constructed from the integers, and they form an ordered field. And the integers can be constructed from the positive integers, just like Nick promised. And oh yeah, I do once again believe in the number 0. Now some quick bonus material. When I took complex analysis, we learned how to compute some really tough-looking integrals on the regular old real numbers, but we used complex analysis to do so. I started to wonder, what if I don't believe in imaginary numbers? Is the argument still valid? Is the answer still pi over 2? I quickly realized that if I didn't believe in the imaginary or complex numbers, I could fudge it. I could construct the complex numbers. It's worth taking a moment to think about how you would do this. What's interesting is that this might be the simplest construction in this whole video. We can use ordered pairs of reals to represent complex numbers. We can then define addition in the obvious way, and define multiplication in a not so obvious way, but it corresponds to the rules you already knew for complex numbers. You'll want to check that numbers of the form x, 0 still multiply and add like real numbers, and you'll have to check to verify about 100 other properties. And that's really all there is to it. You don't need to believe much of anything to solve that integral, even if you have to use imaginary numbers. Thanks for watching, and we hope we've made Dedekind cuts and the construction of number systems more intuitive. Nick really wanted to be here to thank you himself, but he is in my closet computing the decimal expansion of the 7th root of 13, and I may have locked the door from the outside. I told him he could come out when the digits start repeating. As an aside, he's a super smart guy, but he takes forever with the simplest arithmetic assignments like this one. Anyway, if you've enjoyed even a single moment of this video or any of my t-shirts, please click like and subscribe. It really helps us out. I'd like to thank Grant Sanderson and 3 Blue 1 Brown for hosting this contest and for single-handedly making math videos cool. We'll see you next time.